Hello everyone, my name is Yahui and I come from the University of Tokyo. With the co-authors, we are happy to present our research, TensionFab, Fabrication of Room-Scale Surface Structures from the tension-active form of planar modules. TensionFab, a novel technique for creating shape-changeable room-scale structures. This method employs easily available planar materials, such as paper, plywood, MDF, cuts them into 2D shapes, and then connects the pieces manually to create a unified structure capable of 2D and 3D deformations. Constructed TensionFab structures are characterized by easy achievability of target surfaces, substantial structural strength, shape changeability, time and material savings, and easy storage and transportation. In this presentation, it consists of these 6 parts. Recent contributions in human-centered interaction have extended their focus beyond the scale of human hand and body to explore interactions between individuals and their broader environment. Interaction research at room scale over the past few years can be categorized into these 5 groups: interaction systems on wall, floor, ceiling, furniture, and room-scale human gesture recognition. Many of the studies mentioned above were carried out within conventional square rooms, where the existing elements, like concrete walls or structural ceilings, often limit the potential for interactions. In reality, rooms are not always box-shaped. The inherent charm of spatial design is yet to be fully exploited in room-scale HCI. In order to advance this area, we propose a novel approach to infuse holistic principles into space design, along with a user-friendly fabrication method for creating surface structures at a room scale. In an ideal interactive environment, the room elements should be universally connected. The ceiling, walls, floor, and furniture should form a ubiquitous and reconfigurable system, providing humans with a spatial structure that can be controlled and adjusted. The challenge lies in finding a stable, shape-changeable structural system while leveraging materials and construction systems that are easily processed and assembled. To address this challenge, this study introduces the basic principles of TensionFab, a novel category of surface structure characterized by room-scale dimension and shape-changeable, developing a user-friendly design assistance tool for novice, validating the modeling precision and structural performance of fabrication results, offering the proposals of application scenarios in real construction contexts. The related work firstly goes to the 2D to 3D form-making methods. A considerable portion of research in computer graphics has delved into deformation techniques to achieve a target form from an initial planar state. For instance, the inflatable structures, origami and kirigami, bending elongate beams, and auxetic materials. However, these works have their limitations of the requirements of specialized air inflation equipment, significant increases in weight and complexities in large-scale construction, and costly in financial aspects. The structural system proposed in this research is based on truss structures. Both in fields of architecture and HCI, truss structure has been widely used. In our proposal, a planar thin plate is utilized, cut into 2D shapes similar to window frames, and then transformed into truss-like units through frame bending. Principle: a TensionFab module consists of 2 parts, an outer frame and 4 internal arms. Each arm is attached to the frame at one end, while connecting to the opposite arms at the other ends, creating a gap between the linkages. Connecting 2 opposing arms produces a surface similar to settle surface in the 0-degree module. By rotating the 4 arms by 30, 45, and 60 degrees, using the module center as the pivot point. 3 additional distinct shapes can be generated. For ease of observing shape changes, module combinations here are categorized into 2 types. Combination of identical modules involves aligning and arranging the modules of the same size and same rotation degrees in a row. And combinations of different modules replaces pieces of itself with different modules after initially aligning 0-degree modules in a row. In the TensionFab approach, when combined modules being transformed from a 2D shape to a 3D object, they become a structural system similar to a truss. The 2 opposite edges of the outer frame, along with 1 pair of arms, serving as upper and lower chords, are linked together by the other frame edges and arms just like the webs in the truss that the axial forces transmitted in them. The unit thicknesses created between the upper and the lower chords contribute to the overall stiffness of the structure. The figure in the right side is a FEM-based force analysis, highlighting the similarity in tensile and compression distribution in both structural forms. TensionFab can be designed based on target shapes. We use a kangaroo plugin in rhinoceros and grasshopper, a live physics engine for form finding, optimization, and constraint solving. This design process starts with using an elastic grid to be stretched to fit the target surface. Each grid unit is then adjusted to form a saddle surface and combined to fit the target surface. For each saddle surface, the intersection points of the surface principal direction with each frame edge are determined. Drawing a straight line between the intersection points on opposite edges obtains the arm's length, direction, and rotation degrees. Finally, the edge length and angle degrees for the 4 corners of each saddle surface are extracted, generating the basic lines of the planar modules for processing data. We developed 2 interactive design assistant tools based on Grasshopper plugin in Rhinoceros. The second tool assists users in conducting tessellation simulation on a given target surface, optimizing the shape of the modules, and calculating the position and length of the arms in the planar state. Ultimately, the 2D baselines can be exported to the Rhino view for the next step of creating processing data. To evaluate our deployment simulation, we scanned 5 fabrication results and compared them with the target surface using 3D metrology software. The results of D in the figure were obtained by detecting the distance between the scanned body and the target surface. The results show that 75.1% to 96.9% of the points were within the 7.5 mm tolerance. The annulus shape achieved the highest accuracy, with the tolerance exceeding 7.5 mm and only 3 points out of total of 96. To assess the load-bearing capacity of the modules in their combined state, 4 45-degree modules with a thickness of 15 mm were combined to form a flat shape. An adult weighing 75 kg stood on the structure while carrying a box of 16-liter water, and the structure remained sturdy. We use finite element method analysis software to simulate the room-scale pavilion performance. The analysis of the structural response for different geometries suggests that it is possible to create tall structures capable of accommodating people while providing sufficient resistance. The TensionFab's approach, involving the transformation of planar modules into 3-dimensional shapes, offers the opportunity for embedding diverse programmabilities during this transition. In a specific scenario, 3 distinct planar materials, 2D map, moss, and EL sheet, were attached to a planar module. This modular design inspires new ideas for modular architecture design. Potential programmabilities such as information presentation, incorporation of plants, illumination environment, and other interdisciplinary features can be integrated into buildings from the initial stages of architectural construction. Leveraging the load-bearing strength and the shape changeability of TensionFab structures, we propose two application scenarios for functional surfaces, which are supportive surface and sensing surface. Supportive surface structures can function as movement surfaces for small robots like Sony's Toyo. This allows such robots to execute positional transformations such as moving from the ceiling to the wall without surface shift. And the surface can be raised from the ground and transformed into the structure of a specific height, offering versatility for various applications in daily life. The structure can serve as a table, a cushion, a seat, or a step. With sensing devices, the sensing surface structures can be utilized in room-scale installations that interact with surrounding environment as smart facade. The charm of empty space lies in its limitless canvas, inviting boundless exploration and the creation of infinite possibilities. By utilizing TensionFab structure modules, such as 2 mm thick plywood board, various spatial configurations can be achieved through shape-changing mechanisms. An adaptive pavilion measuring approximately 6.8 meters in length and 2.8 meters in height can be swiftly constructed for pop-up event. A kinetic gate designed for stage performances can dynamically change shapes in real time, enhancing the theatrical experience by reacting to the storyline and actor performances. Leveraging the TensionFab approach, users can fabricate surface structures to accurately achieve target shapes, presenting a practical strategy for creating representative spaces. This versatility allows applications in diverse fields such as movie scene design, performance stage design, interior design, and education model making. For example, the structure in picture shows the example of an education tool for spatial study, effectively representing the characteristics of a black hole. This research highlights several directions for further exploration in design assistance tool, material, structural strength enhancement, automation, mechanical metamaterial structure, and tangible space. It outlines potential research challenges and opportunities for advancing this research in the future. In this paper, we proposed TensionFab, a new approach to designing and fabricating room-scale surface structures with shape-changeable features. This technique uses easily available planar materials and cuts them in 2D to create 2D to 3D deformations by humanly connecting joints. We introduced the basic principles of shape generation and deformation, module assembly, and the structural system of this method. In order to make it accessible to users without construction and engineering experience, we developed an interactive design assistance tool based on the Rhinoceros platform. We also evaluate the physical stresses on fabricated structures together with the structural performance using specialized architecture engineering software. Finally, we produced a variety of constructs with actual construction and proposed scenarios that can be applied. It is expected that this study will inspire more researchers to explore the room-scale interactions in the field of HCI. Thank you for your attention. Please check our paper for more details.